Okay, I'm going to have to hustle here, I think. Now, in this series, I'm presenting reasons to believe God exists that do not depend on the Bible being true. And so far, I've argued that the existence of the universe implies God's existence. Objective morality requires God's existence. Free will and free thought require God's existence. And in this morning's class, my contention is it's more reasonable to believe that no living organism arose by purely natural processes from non-living matter than to believe that it did. And it is more reasonable to believe that the origin of living organisms involved input from an intelligence than to believe that it did not. Now, according to the atheist, the first living cell arose by purely natural processes from non-living matter. And then all subsequent life forms descended from that first living cell. In other words, that first cell is the great grandparent of everything that has ever lived on earth. And the vast differences between life forms, say between a sponge, an apple tree, a bumblebee, and a whale, the vast differences between the life forms are allegedly due to the gradual accumulation of small changes in the branching lines of descent, as you see represented here. All of these branching lines of descent, we start with this first cell, and then they all, as things descend over time, vast number of generations, these changes accumulate. That's the idea of how that happened. That's how, that's their claim. Now this claim about how life diversified after the arrival of that first cell is its own fairy tale. But my focus right now is on the origin of that first living cell. From as early as Aristotle in the 4th century BC, people believed in the spontaneous formation of living organisms. They thought rats, all kinds of things, could just come out of non-living matter. In other words, they thought that living things could arise from dead, non-living matter. And belief in the spontaneous generation of insects. So the larger things, that belief faded, but belief in the spontaneous generation of insects, that continued until 1688, when an Italian physician and biologist, Francesco Redi, he showed that maggots didn't appear in rotting flesh if the jar containing the meat was covered with gauze. In other words, if you kept flies from landing there and doing things there. So he showed that. But even after that, people continued to believe that microscopic life, that arose spontaneously. It was in the middle of the 19th century. The middle of the 19th century, the French Academy of Sciences, they offered a prize to anyone who could prove experimentally that microscopic life either did or did not arise spontaneously from non-living matter. And Louis Pasteur designed an experiment that showed that not even microscopic life would arise in a bottle of boiled meat broth if it was protected from particles entering it from the air. So that simple experiment seemed to close the door completely on the possibility of spontaneous generation of life. Life only comes from life. It doesn't come from non-living material. But the atheist has no choice but to believe that life on at least one occasion arose spontaneously from non-living matter to get that first cell that's necessary to kickstart their alleged evolutionary process of diversification. They've got to get life and replication to kickstart this chart here. So they have to believe that at least on one occasion, life arose spontaneously from non-living matter by purely natural processes. Now, the living world, it contains two fundamentally different types of cells. You have prokaryotes and eukaryotes, and prokaryotes, of which common bacteria are the prime example, they are simpler than eukaryotes in that they don't have a nucleus or other organelles, but they are far from simple. They are far from simple. On the contrary, these things have an insane degree of integrated complexity. You know, back in the day, people could think, well, it's just this little blob. No longer. You see, microbiology and these things have changed that thing. And you can see, man, these things have an insane degree of integrated complexity. They're like a microscopic factory that's operating in accordance with a sophisticated computer program. Now, let me back that up with some quotes, because I tell you that and you say, well, who are you? Well, let me show you where I get these kinds of ideas. Michael Denton, he's a developmental biologist and a genetics researcher. He observed decades ago in a book he published in 1986, he said molecular biology has shown that even the simplest of all living systems on the earth today, bacterial cells, are exceedingly complex objects. Although the tiniest bacterial cells are incredibly small, weighing less than 10 to the minus 12th grams, each is in effect a veritable micro-miniaturized factory containing thousands of exquisitely designed pieces of intricate molecular machinery made up altogether of 100,000 million atoms, far more complicated than any machine built by man and absolutely without parallel in the non-living world. James Shapiro, he's a Cambridge-educated professor of biochemistry and molecular biology at the University of Chicago. Well, he wrote decades ago, he said, although bacteria are tiny, they display biochemical, structural, and behavioral complexities that outstrip scientific description. In keeping with the current microelectronics revolution, it may make more sense to equate their size with sophistication rather than with simplicity. Harold Klein, he was the chairman of the National Academy of Sciences committee that reviewed the origin of life research in the early 1990s. And Harold Klein said, the simplest bacterium is so darn, he said something else, but is so darn complicated from the point of a chemist that it is almost impossible to imagine how it happened. So that's what Klein says. Alonso, Ricardo, who's a biochemist, and John Szostak, who is a Nobel Prize-winning geneticist, he won his Nobel Prize in medicine, they said in 2009, every living cell, even the simplest bacterium, teems with molecular contraptions that would be the envy of any nanotechnologist. As they incessantly shake or spin or crawl around the cell, these machines cut, paste, and copy genetic molecules, shuttle nutrients around or turn them into energy, build and repair cellular membranes, relay mechanical, chemical, or electrical messages. The list goes on, and new discoveries add to it all the time. Now, the simplest conceivable cell, it requires a membrane, something to separate it from it and protect it from the surrounding environment. And this membrane, it's something sophisticated. It's a sophisticated and complex structure that has channels and pumps that move select molecules in and out of the cell. They're like portals on a spaceship. You know, you see on these, open up and let something in, not let the wrong stuff in, open up and let these things out. They're like portals on a spaceship, and in addition to the membrane, the simplest conceivable cell must have hundreds of different proteins, an array of nanomachines that carry out all kinds of essential functions in the cell, and instructions for replicating and for carrying out all the other operations in the cell. I mean, it's absolutely mind-boggling. It truly is staggering, the complexity of these things. And in thinking about the difficulty of having a cell arise spontaneously in the wild by purely natural processes, and thinking about that, the first place, the place to start is to recognize that all of the building blocks, the basic chemical building blocks, we don't even know how those things could have arisen on a prebiotic earth. Those fundamental chemical building blocks. We don't even know how they could have arisen. You see? The simplest conceivable cell, it requires 4 classes of molecules. It requires nucleic acids, amino acids, carbohydrates, and lipids. And these things are going to get connected into large chains. But you at least have to have those fundamental classes of molecules. And those molecules, they come in what they call chiral forms. In other words, you have a left-handed and a right-handed form of the molecule. These non-superimposable mirror images, like gloves. Okay? So they come in these different forms. But since only the left-handed form works in living things, the right-handed forms would have to be filtered out for the molecules to be used in the construction of a cell. So we can't have all of these left and right-handed forms there. They're made in both forms, but somehow this form's got to get screened out. And as James Tour, who's a synthetic organic chemist, he's the T.T. and the W.F. Chow Professor of Chemistry at Rice University. Tour has over 700 research publications. He has over 140 patents. And if you can go on the internet, by the way, on YouTube, and look up James Tour and the Origin of Life and listen to anything he has to say. But Tour says about the origin of life, he says, remember, we need 4 classes of molecules. We need the nucleic acids, and then the homochiral systems for the amino acids, which then need to be built up into protein structures. I'll talk about that in a minute. It says we need the carbohydrates, which have to be built up into polycarbohydrates. So you get the carbohydrates, and they have to be linked together into these carbohydrate structures. And then we need the lipids, which are also chiral, meaning they come in these 2 glove forms. All right, he says all of these we need in homochiral form. In other words, we need them where we only have the one form. The other forms screened out or eliminated. He says we don't know how to do this in any prebiotic type scenario at all. These have not been made. Now that's not what you hear. You know, I know what biology textbooks at lower levels, high school biology books and this kind of stuff tell you. But that's not how it works in prebiotic conditions. Now, setting aside this massive problem of these chemical building blocks arising spontaneously in the wild, which we don't know how that would happen, and setting aside the difficulty not only of having them arise, but then having them be collected in the same place, I want to focus on just one piece of the origin of life puzzle. Just one piece of that. The need for hundreds of different proteins. That's why I want to concentrate on that. Now, proteins, they're the workhorse molecules of life. They're the workhorse molecules of life. They take part in virtually every cell structure and every cell activity. The zoologist Ann Gager, she wrote in 2012, she said, proteins are the building blocks of life. They are the structural parts that give cells shape. So they're the materials, the building materials, the enzymes that build or break down the molecules of life, the motors that transport things, the agents that send signals and regulate the activity of other proteins and genes, and the morphogens that help determine the development of the organism. Now, we know that hundreds of different proteins are necessary for the simplest conceivable cell. You say, well, how do you know that? Well, we know that because of experiments on this tiny bacterium, Mycoplasma genitalium, which has the fewest genes of any organism we know of that's able to perform the standard functions of life on its own. Now, it's a parasite, but it only uses the host for food and housing. With the food, it can perform the standard functions of life on its own. So it's not like some other parasites that can't do that. But so it has the fewest number of genes. And so genes, as I'll explain in a minute, genes code for these proteins. It has the fewest number of genes. So what people did is say, well, how many genes do you absolutely have to have a living cell? So they go into this small organism with the fewest number of genes we know of, and they start knocking out or disabling genes. Okay, so when you disable this protein coding gene, the protein that it codes for is not there. So then I know it has to have that protein. I disable this gene, it doesn't get that protein, it dies. I say, okay, that's essential. So that protein it's got to have. I disable the next one, it doesn't die. I say, okay, that one's not essential. So that's what's been done. And from that they find out that there are 382 of the protein coding genes of Mycoplasma genitalium that are essential. Now that understates the number that you need. It understates it because it doesn't take into account what is known as synthetic lethality. You say, well, what is that? Well, if I disable gene number 1, it dies. I say, okay, so I know that I then have to have that gene's essential. I disable gene number 2, it doesn't die. I disable gene number 3, it doesn't die. I say, okay, 2 and 3 aren't necessary. But if I take out 2 and 3 together, both of which independently are not essential, but if I take them out together, it dies. All right, they don't account for that. But ignoring that, all right, so the 382 understates how many proteins are necessary. But you have 382 experimentally determined, but you still have people say, well, look, we think we could get the number down lower than that. So they speculate. They say, no, in a hypothetical organism, we think we could get the number down. Okay, but nobody thinks you could get it down below 200 or 300 proteins. Even in a hypothetical, speculative organism, everybody's on board. You're going to need 200 or 300 proteins if you're going to have a living cell. Now, to appreciate the difficulty of this requirement of having hundreds of proteins, to appreciate the difficulty that this poses for the spontaneous generation of life, you need some idea of what proteins are and how they're manufactured in a cell. So you're going to have to bear with me. This isn't conceptually difficult. Okay, but bear with me. And it takes nerve to do this with a cell biologist sitting right in front of me. Okay? So, if Dr. Glenn starts throwing things, well, then that's your clue that I've gone off the rails. But now proteins, they're made up of small molecules called amino acids that are linked together like beads on a necklace. Okay, they're linked together, a chain of these amino acids. That's what a protein is. Now, I say it's on a long necklace. And I say that because a protein can have anywhere from 50 to thousands of these amino acid beads strung together. Okay, so it's a long necklace, 50 to thousands of these things that are there that form a protein. And with rare exception, there are 20 different amino acids that are used in living things. 20 different amino acids, and the specific order or the arrangement or the sequence of these amino acids on these chains of proteins, the specific arrangement is what determines the protein that you have. Okay, so I've got 20 amino acids in living things. I've got chains of sequences of amino acids that are proteins. So let's say protein A is 100 beads long. It's the arrangement. I arrange them in a certain order, I get a certain kind of protein. Protein B, they're arranged in a different order, I get a different protein. So the 20 different amino acids are arranged in different sequences, and the sequences of their arrangement on the necklace is what determines the kind of protein that you have. And so you can think about it, since you have 20, right? You have 20 amino acids, you can think about them as letters. At least this kind of stuff helps me. So you have 26 letters in the English alphabet, right? And we arrange those letters to spell sentences and things like that. Well, think of the 20 amino acids that are arranged in certain orders to spell certain proteins. So you have a 20-letter alphabet, and it can be arranged to spell out correctly a protein. Now, if you misspell it, you don't get the protein. They have to be arranged in the right order. And remember, we're talking about an order of 50 to thousands of characters long. And they have to be in that right order. You say, well, if the 20 amino acids, if they have to be arranged in different, precise ways to spell out the hundreds of different proteins that are necessary for the simplest life, how did that happen? How did that happen? Put differently, how do the beads on these proteins get strung in the right order on the hundreds of different protein necklaces that are necessary? Well, in a cell, the ordering of the amino acids into the right sequences so that you actually get a functioning protein, in a cell, that's determined by the cell's genetic material. Deoxyribonucleic acid, or DNA for short. Now, DNA, don't panic. Look, I'm telling you, conceptually, it's pretty straightforward. But when you see things like adenine and thymine, you start glazing over. Okay, but DNA, see, it's made up of molecules that are called nucleotides or nucleotide bases. Okay, so we got the proteins over here, and they are long chains of amino acids in certain sequences. Their order is determined by the DNA. That's going to be over here. Okay, so DNA is made up of these sequences of nucleotides that are linked together like beads on a super long necklace. A super long necklace, you see. And they're actually, as you can see here, they're actually like a ladder structure. You see here are the rails, and you see these different nucleotides in pairs. They correspond and they're paired up, so it's like this. All right? And then you twist it, and that gives you the classical double helix that you're seeing over here on that side. But I want you to ignore part of this, okay? For our purposes, you could just consider we're just going to take this and strip it away, and just consider this as this side, this rail, and this arrangement of nucleotides as just a necklace of beads. Okay, just like on the proteins, there are necklaces of beads of amino acids. Now on the DNA, we've got a necklace of beads of nucleotides. All right, and the order or the arrangement of the nucleotides on the DNA determine the arrangement of the amino acids on the proteins. Okay, you say, well, how does that happen? What's the connection? How in the world does the arrangement of nucleotides on that necklace, the DNA necklace, how does it happen to determine the arrangement of amino acids on the protein necklaces? Well, it's just part of this insanity of the cell. You've got nanomachines at work here. You see, what happens is, well, I did this to make it easier. Instead of the names of the different nucleotides, if you just think of them as 1, 2, 3, and 4, right? 1, 2, 3, and 4. And so they are arranged, these things are then arranged in different orders. So like you see here, I have 414, 314, 22, and we could keep going. So just think of them this way. Instead of worrying about adenine and thymine and this kind of stuff, if you just think of there are only 4 of them. And let's just call them number 1, number 2, number 3, and number 4. And they are arranged in a certain sequence in a certain order. And so what happens is there is a machine that comes in and unwinds this thing, and it goes over in the cell, and it reads the order of these nucleotides, this stretch of nucleotides, opens it up, and a machine comes and makes a copy of that. Then another little nano machine transports that copy that's been made over to yet another nano machine. And this nano machine takes that copy and it goes in, and reading this thing, it sits here and says, okay, I've got 414. They're done in triplets, like area codes. Area code 414 tells me add amino acid X. Area code 314 tells me add amino acid Y. So as it reads this code, it's told when you're making the protein, now add this one, add this one, add this one, add this one. And this is what you have here. You see it goes over to this ribosome, and it winds up manufacturing, stringing together the amino acids based on that copy of the sequence of the nucleotides that it's just made. Do you understand that? That's not, okay. I mean, it seems conceptually pretty straightforward. I'm getting somebody no. But it's just you have a sequence here. I'm taking that sequence. That sequence is read by something to say, okay, these 3, this order of these 3, this codon, this triplet, this area code, tells me add this specific amino acid. The next triplet tells me add this specific amino acid. And this is how it codes for the construction of the different proteins there. So, let me give you this. See if this helps. All right? This is my attempt at this. Now, let's say we have a protein that has only 48 amino acids. I told you that proteins run 50 to thousands. But let's say we got a really short protein that has only 48 amino acids. And this protein is called, this is very short for a protein, but it's just an example, okay. That's the name of this protein. Okay? It has, each one of these letters is a different amino acid. And if they're spelled out correctly, then you get the protein. If it's misspelled, you don't get the protein. All right, well, what's happening with the nucleotides? Well, let's say the nucleotides, these triplets, these area codes of nucleotides, let's say remember there's only 4 of them, so it's 1, 2, 3, or 4. 133, let's say it codes for amino acid A. 142, it codes for amino acid B. 122, and you see the idea, right? All right, so then for the stretch of nucleotides, the DNA, to code for this 48 amino acid protein, this would be the sequence, right? It would be all of these numbers. I just colored them so you could see the triplets. But it's this whole string of numbers. Because the 111 would give you the T. The 112 would give you whatever, the H. All right? The 114. So you'd have all of these. So the point is, you see that to get the amino acids in the proteins in the right order, since they're being coded for by the order of the nucleotides in the DNA, then you see that, well, then the nucleotides in the DNA have to be in the right order. because that's what's determining the order of the amino acids in the proteins. So now we're going to have a really, really long chain of things that are in the right order on the DNA, right? Otherwise, it won't be able to code for all the proteins we need. If we need 100 proteins that have so many amino acids, well, then all of that has to be in the right sequence on the DNA. Somewhere on that DNA, we have to have all of those things in the right sequence, so they can then tell the ribosome, build this particular protein. Okay? I hope you get that. Now, since the amino acids on that protein necklace, they've got to be precise. Like I say, you have to have the precise number. It's like every protein. Let me put it this way. Every protein has a gigantic PIN number. We know what PIN numbers are, right? You want to get into your bank account? What's your PIN number? Blah, blah, blah. If you don't get the PIN number, you don't get in. Well, that's what this is like. Okay? This protein has this PIN number. And if you don't get this PIN number, if the nucleotides are not arranged in 111, 112, 113, 114, 113, all the way down, you're not getting that protein. And you need hundreds. So I hope I'm going through all this because if I just say it, I want you to grasp the immensity of the problem. Okay? It's crazy. So that's it now. So even if you ignore this problem of actually forming nucleotides on Earth that Tour was talking about and getting them collected in the same place, how could the nucleotides of the DNA in the first cell, how could they have been properly arranged, put in the right order so as to be able to serve as a template for the manufacture of the hundreds of proteins that are necessary for the minimal cell? How would the nucleotides ever get arranged in that right sequence to be able to code for all of those different proteins? It's just a crazy thing, right? If you have looked the nucleotides, if you have 250 proteins, okay, so everybody says you got to have at least 200 or 300. Actually, 382 was the minimum. More than that should be. But no, people say hypothetically we think we get down to 2 or 3. All right, let's go 250. If we say there's an average of 300 amino acids per protein, and I need 250 proteins, well, then I got to have 75,000 amino acids in the right sequence, right? And what does that translate into? And well, then how many nucleotides do I have to have in the right sequence to be able to code for those 75,000 amino acids? Well, remember they're in triplets. So then I got to have 3 nucleotides per amino acid. So I got to have 225,000 nucleotides in the right sequence to be able to serve as a template for producing 250 proteins on an average of 300 amino acids each. Now, how am I going to get 225,000 nucleotide bases in the right order? If I gave you marbles 1, 2, 3, and 4, and I said you got to arrange 225,000 of them in the right order, do you think that would happen? It would only happen if you were directing them. You'd be sitting there forever going, didn't get it. Didn't get it. You see, so you have to have that. Now, you say, well, how do these things get arranged this way? Well, in answering that question, it's crucial to note that the sequence or the order of these nucleotides of DNA, it's not determined by chemistry. Okay, in other words, chemistry doesn't care if it's nucleotide 1, 2, 3, or 4. It doesn't determine the arrangement. So you can't say, well, they're going to get set that way by some law of chemistry. No, it's not. They're freely substitutable. And so that's not something that you can look for. There's no chemical reason why they would be in the proper order to enable them to serve as a template for all those proteins. Okay, so you say, well, how did they get into the right order? Chance certainly can't explain it. Right? Chance, there's no way to explain it. Oh, I'm going to run out of time big time here. Okay. But chance, you see, chance can't explain this at all, because as Meyer says, I'm just going to skip this and just tell you, the point of that quote is that, look, when you're trying to compute the odds of chance of coming up with proteins or the nucleotide sequences, I can look at either the odds of randomly constructing the protein or the odds of randomly generating the nucleotide sequences. They're compatible, so it's easier to just look at the odds of, what are the odds that I can randomly get a protein of 100 amino acids? Well, I've got 20 amino acids to choose from, right? So in the first lot, I'm going to have 100. The first bead, I got a chance of what? 1 out of 20. Second bead, I got a chance of 1 out of 20. Third bead, 1 out of 20. And you have to multiply all these together. So what it turns out to be is when you say, well, what are the odds of randomly assembling 100 amino acids in the right order? Well, you wind up the protein of 100, the odds are 1 in 10 to the 130th power. Okay, that's a big number. That's a 1 over a 1 followed by 130 zeros. You see, that's a big number. It's thought that there are only 10 to the 65th power atoms in our galaxy. You beginning to see this? Thought that there's only 10 to the 80th atoms in the universe. And so you see that odds, randomness isn't going to do that. Now, what Axe did, Douglas Axe, he said, look, there's some room for variation in the order of the amino acids on the proteins. Not much, but there's some. So he says, I'm going to bend over backwards. I'm going to ignore all the amino acids that aren't part of the 20 that are used for life. I'm going to ignore the fact that we only need homochiral, the left-handed form. Ignore all that. And I'm going to say, okay, you can substitute some of these. You still wind up with, allowing for variation in the amino acid order, being very conservative in that, you still wind up with an odds of constructing and a protein of 100 amino acids to be 1 in 10 to the 65th power. Okay? And that's why I said it's thought there's 1 in 10 to the 65th atoms in the galaxy. So if I told you I've color-coded one atom in the galaxy, what are the odds on you hitting it? Well, it's pretty small. You'd be throwing and picking the rest of your life. And it wouldn't make a difference because the odd's so big you're never going to hit on it. All right, so that's what's going on. Now you say, well, I say it's more reasonable to believe that the origin of living things, so that's the idea that these things could arise spontaneously, that you could get 200 or 250 or 300 proteins randomly assembling, is crazy. And you say, well, what about this thing? Why do you think that it says that an intelligence must be involved, or it's more reasonable to think an intelligence is involved? Well, I think that because when we see these kinds of things, you see that the order of these nucleotides on the DNA, it's functioning like computer code. In other words, it's giving specified information into a complex material area, and that it's directing what's going on in there, and it's just like a computer code. In fact, Dawkins said the machine code of a gene is uncannily computer-like. Bill Gates, Mr. Microsoft, he says human DNA is like a computer program, by far, far more advanced than any software ever created. Hubert Yockey, he says it's highly relevant to the origin of life. The genetic code is constructed to confront and solve the problems of communication and recording by the same principles found both in the genetic information system and in modern computer and communication codes. Now, when you're thinking of a computer code, do you think that randomness can produce word? You think I just think I can just throw ones and zeros together and I'm going to come out with word? You recognize that's not going to happen. You recognize that what is required for that is the intelligent placement with an understanding of what is needed and what needs to go where. Every time we see this kind of specified complexity, every time we see specified complexity and we trace the origin of it, it is always an intelligence. That's why you remember SETI, Search for Extraterrestrial Intelligence. The whole thing is built on that fact. Because in that movie Contact, where everybody flips out when they get a radio signal that is a long series of prime numbers, they all go crazy and they say, that came from an intelligence. You say, why do you think that came from an intelligence? Because it's specified complexity. It is prime numbers. It's not just a random array. It is something that has an independent target, an independent relevance apart from simply the sequence of the numbers. So as soon as you get this long sequence of prime numbers, everybody goes, oh, we have evidence of an intelligence. That's what I'm telling you. Every time you see specified complexity and you get to the source of it, it's an intelligence. Well, here we have specified complexity in DNA. And so I say it's more reasonable to conclude, just like every other time we see specified complexity, that it indicates the involvement of an intelligence. When I see specified complexity in DNA that codes for all of these proteins, it is more reasonable to understand that it indicates an intelligence was involved. Okay? So that's what I'm getting at. Now I want to end here. I've got 2 minutes. I raced through that because I was paranoid that I wasn't going to finish. But let me leave you with on this origin of life. Let me say one other thing about it real fast and point out the mother of all vicious circles. And that's that proteins are essential for a living cell, and proteins are produced from this DNA template, as I have so expertly explained to you. Right? So these proteins are produced from this DNA coding, but the kicker is that many proteins are necessary to produce proteins from the DNA template. In other words, you got to have proteins in order for the DNA template to actually manufacture proteins. In other words, it's like you have to have steel in order to manufacture steel. Well, then how do you get steel in the first place? How would that ever happen? You say, well, that's just crazy preacher talk. Let me end with this. Okay, by the way, Anthony Flew, about what I was telling you about the coding and the, computer stuff, Anthony Flew, very well-known atheist philosopher. And in, I think, 2004, after having spent his life arguing for atheism, he said the findings of more than 50 years of DNA research have provided materials for a new and enormously powerful argument to design. That's what I was trying to give you some sense of. I hope I didn't mess that up. All right. So this idea of if you need steel to make steel, how are you ever going to get steel? If you need proteins for the DNA template to actually be transformed into proteins, how are you ever going to get proteins? So here's Karl Popper, who is a very well-known philosopher of science. Popper says, what makes the origin of life in the genetic code a disturbing riddle is this: the code can't be translated except by using certain products of its translation. This constitutes a really baffling circle, a vicious circle. It seems for any attempt to form a model or a theory of the genesis of the genetic code. David Goodsell. Now, Goodsell is a biochemist. He wrote in 1998, almost through here. He says, this is one of the unanswered riddles of biochemistry. Which came first, proteins or protein synthesis? If proteins are needed to make proteins, how did the whole thing get started? Last one I'll give you. Robert Shapiro. He says he was a professor of chemistry at NYU. Shapiro says, DNA replication cannot proceed without the assistance of a number of proteins, members of a family of large molecules that are chemically different from DNA, as you now know very well, right? All right. It says, the above account brings to mind the old riddle, which came first, the chicken or the egg? DNA holds the recipe for protein construction, yet that information can't be retrieved or copied without the assistance of proteins. Which large molecule then appeared first in getting life started? Proteins or DNA? I said that was the last one, but I lied. I want to read you two more. I see I'm over time, but let me do this. I'll skip this one. This was Harold Urey. I had two. Harold Urey is a chemist, Nobel Prize-winning chemist, who was involved with Stanley Miller in the 1952 Miller-Urey experiment, which was a big deal for origin of life research, so they said. In 1962, he made this statement. I'm going to skip it. I wanted to fast forward 59 years after the Miller-Urey experiment. In 2011, Eugene Koonin, very well known. Koonin is a well-known, let me see what his particular field is. He's a molecular biologist. Last thing, 2 slides, then I truly will shut up. He says the origin of life, this is 2011, molecular biologist Eugene Koonin, very well known. He says the origin of life is one of the hardest problems in all of science, but it is also one of the most important. Origin of life research has evolved into a lively interdisciplinary field, but other scientists often view it with skepticism and even derision. This attitude is understandable and in a sense perhaps justified given the dirty, rarely mentioned secret, despite many interesting results to its credit when judged by the straightforward criterion of reaching or even approaching the ultimate goal, the origin of life field is a failure. We still do not have even a plausible, coherent model, let alone a validated scenario for the emergence of life on Earth. Certainly this is not due to a lack of experimental and theoretical effort, but to the extraordinary intrinsic difficulty and complexity of the problem. A succession of exceedingly unlikely steps is essential for the origin of life, from the synthesis and accumulation of nucleotides to the origin of translation through the multiplication of probabilities. These make the final outcome seem almost like a miracle. Thanks for hanging with me.